Excessive impurities in mixing water not only may affect setting time and concrete strength, but also may cause efflorescence, staining, corrosion of reinforcement, volume instability, and reduce durability. Some impurities may have little effect on strength and setting time, yet adversely affect durability and other properties. The following slides contain a synopsis of the effects of certain impurities in mixing water on the quality of normal concrete. Carbonates, bicarbonates of sodium and potassium have varying effects on the setting time of different cements. Sodium carbonate can cause very rapid setting. Bicarbonates can either accelerate or retard the set depending on the chemistry of the cement used in the concrete. In large concentrations, these salts can materially reduce concrete strength. When the sum of the dissolved salts exceeds 1,000 ppm, tests for their effect on setting time and 28-day strength should be made. The possibility of aggravated alkali aggregate reactions should also be considered. Concern over a high chloride content in mixing water is chiefly due to the possible adverse effect of chloride ions on the corrosion of reinforcing steel or pre-stressing strands. The acid-soluble chloride ion level at which steel reinforcement corrosion begins in concrete is about 0.2% to 0.4% by mass of cement. Placing an acceptable limit on chloride content for any one ingredient, such as mixing water, is problematic considering the variety of sources of chloride ions in concrete. An acceptable limit in the concrete depends primarily upon the type of structure and the environment to which it is exposed during its service life. Concentrations of 20,000 ppm of sodium chloride are generally tolerable in concrete that will be dry in service and has low potential for corrosive reactions. The ACI 318 Building Code and CSA Standards A23.1 limit water-soluble chloride ion content in reinforced concrete to the following percentages by mass of cement. For pre-stressed concrete, 0.06%. For reinforced concrete exposed to chloride in service, 0.15%. For reinforced concrete that will be dry or protected from moisture in service, 1%. And for other reinforced concrete construction, 0.3%. Concern over a high sulfate content in mixing water is due to possible expansive reactions and deterioration by sulfate attack. Although mixing waters contain 10,000 ppm of sodium sulfate have been used satisfactorily, the limit in ASTM C1602 3,000 ppm should be considered unless special precautions in the composition of the concrete mixture are taken. Salts of manganese, tin, zinc, copper, and lead in mixing water can cause a significant reduction in strength and large variations in setting time. Of these, salts of zinc, copper, and lead are the most active. Salts that are especially active as retarders include sodium iodate, sodium phosphate, sodium arsenate, and sodium borate. Generally, concentrations of these salts up to 500 ppm can be tolerated in mixing water. Another salt that may be detrimental to concrete is sodium sulfide. Even the presence of 100 ppm warrants testing. Acceptance of acid mixing water should be based on the concentration in parts per million of acids in the water. Generally, mixing waters containing hydrochloric, sulfuric, and other common inorganic acids in concentrations as high as 10,000 ppm have no adverse effect on strength. Acid waters with pH values less than 3.0 may create handling problems and should be avoided if possible. Waters with sodium hydroxide concentrations of 0.5% by mass of cement do not greatly affect concrete strength, provided quick set is not induced. Higher concentrations, however, may reduce concrete strength. Potassium hydroxide in concentrations up to 1.2% by mass of cement has little effect on the concrete strength developed by some cements, but the same concentration, when used with other cements, may substantially reduce the 28-day strength. The possibility for increased alkali aggregate reactivity should be considered. Most waters carrying industrial waste have less than 4,000 ppm of total solids. When such water is used as mixing water in concrete, the reduction of compressive strength is generally not greater than 10% to 15%. Wastewaters such as those from tanneries, paint factories, coke plants, and chemical and galvanizing plants may contain harmful impurities. It is possible to test any wastewater that contains even a few hundred parts per million of unusual solids. About 2,000 ppm of suspended clay or fine rock particles can be tolerated in mixing water. Higher amounts might not affect strength, but may influence other properties of some concrete mixtures. When cement fines are returned to the concrete and reused washwater, 50,000 ppm can be tolerated. The effect of organic substances in the setting time of Portland cement or the ultimate strength of concrete is a problem of considerable complexity. Such substances, like surface lumes, can be found in natural waters. Organic impurities are often a humus nature containing tannates or tannic acid. The effect of tannic acid on concrete strength is shown in this graph. A typical sewage may contain about 400 ppm of organic matter. After the sewage is diluted in a good disposal system, the concentration is reduced to about 20 ppm or less. This amount is too low to have any significant effect on concrete strength. Small amounts of sucrose usually retard the setting of cement. The upper limit of this range varies from different cements. The 7-day strength may be reduced while the 28-day strength may be improved. Sugar, in quantities of 0.25% or more by mass of cement, may cause rapid setting and a substantial reduction in 28-day strength. Mineral oil not mixed with animal or vegetable oils may have less effect on strength development than other oils. However, mineral oil in admixture in concentrations greater than 2.5% by mass of cement may reduce strength by more than 20%. Oils may interfere with the action of air-entraining admixtures. Water containing algae is unsuitable for concrete because the algae can cause an excessive reduction in strength. Algae may also be. When evaluating a water source for its effect on concrete properties, it is important to also test the water with chemical admixtures that will be used in the concrete mixture. Certain compounds on water can influence the performance and efficiency of certain admixtures. For example, the dosage of air-entrained admixtures may need to be increased when used with hard waters containing high concentrations of certain compounds or minerals. In summary, we discussed the standards for mixing water for concrete and the sources from which we obtain mixing water. We then went through a summary of the most common impurities and their effects on concrete. We ended the discussion with a brief mention of the interactions between mixing water with impurities and chemical admixtures. Please write down any questions you may have in your journals to bring and discuss in our next class.